In today's lecture, we will address the mixed integer linear programming problem called MILP, and we will see algorithms to solve the MILP problem. So, we start with a numerical example. So, the example that we will use is a maximization problem. So, this is the example. We use a slightly different notation here. We have used both x and y as variables. Because a mixed integer linear programming problem has some variables that have to be integers and some variables that can take continuous values, it is good to use a notation by which the x variables represents the continuous variables and the y variables represent the integer variables. So, in this particular example we have two variables, one of which should take only integer value, which is y1. So, y1 greater than or equal to 0 and integer. The other variable x1 can take continuous values. So, if we had more than one x variables, then we use x1, x2 and so on. Similarly, we use y1, y2 and so on. We will be looking at three different algorithms to solve this. We will begin with a branch and bound algorithm, then we will look at a cutting plane algorithm for the MILP, and later we will look at Bender's partitioning algorithm to solve MILPs. So, let us begin with the branch and bound algorithm. So, as is customary with branch and bound for all integer programming, we first solve the LP by relaxing the integer restriction on the y variable. So, we treat y also as greater than or equal to 0 to begin with and solve a linear programming problem. If for some reason the optimum solution to the linear programming problem gives y1 an integer value, then it will be optimal to the MILP. If it is not, we will then do something to try and get the integer value to y1 and the corresponding optimal solution. So, let us first solve the problem as a linear programming problem to see what is the LP optimum solution. So, we set up the simplex table as we have done before. It is a maximization problem. So, we will add two slack variables which are called x3 and x4. Now, because x1 is continuous and only y1 is restricted to an integer value, x3 and x4 will be continuous variables. So, they will not be integer variables, they will be continuous variables. So, x3 and x4 which are continuous variables, we will start with them as the basis. So, we start with x3 and x4 and then we have minus x1 and minus y1 here as currently non-basic variables. So, we will have minus 3 and minus 2 here, we will have 6, 1 and 1, and then we have 20 and then 5 and 2. So, this is the initial simplex table with x3 and x4 as basic variables and x1 and y1 as non-basic variables. So, this solution is primal feasible and dual infeasible. Dual has negative values. So, the most negative dual will enter, which is equivalent to the largest coefficient rule, where the most positive Cj minus Zj or the most negative Zj minus Cj will enter for a maximization problem. So, the variable x1 will enter the solution and then we find out the minimum ratio. 6 divided by 1 is 6, 20 divided by 5 is 4. So, this will be the leaving variable and this will be the pivot. So, the next iteration will be like this. So, minus x4 and minus y1, x3 and x1. Pivot becomes 1 by pivot So 1 by 5, divide by the pivot 4, 2 by 5, divide by negative of the pivot, so plus 3 by 5 and minus 1 by 5. Now this is initially taken as 0. So 0 minus 3 into 4 is plus 12, 6 minus 1 into 4 is 2, this is minus 2 minus 3 into 2 by 5, which is minus 2 plus 6 by 5, which is minus 4 by 5, minus 2 plus 6 by 5 is minus 4 by 5, 1 minus 1 into 2 by 5 is 3 by 5. So once again this is primal feasible, dual infeasible. So the negative dual will enter, there is only one entering variable, so variable y1 enters the solution. Now to find out the minimum ratio, 2 divided by 3 by 5 is 10 by 3, 4 divided by 2 by 5 is 10, so x3 will go, y1 will enter. So the next iteration will have y1 will enter, so minus x4 minus x3 y1 and x1, this is the pivot. So pivot becomes 1 by pivot 5 by 3, divide by the pivot 10 by 3 minus 1 by 3, divide by negative of the pivot, so minus 4 by 5 divided by minus 3 by 5 is plus 4 by 3, minus 2 by 3, so this will be 12 minus 4 by 5 into 10 by 3, so 12 plus 40 by 15 or 12 plus 8 by 3, 44 by 3, four minus 2 by 5 into 10 by 3 is 4 minus 4 by 3, which is 8 by 3. Three by 5 minus 4 by 5 into minus 1 by 3. So 3 by 5 minus 4 by 15 is 5 by 15, which is 1 by 3. One by 5 minus 2 by 5 into minus 1 by 3. So 1 by 5 plus 2 by 15, 5 by 15, which is 1 by 3. So this is the LP optimum. With x1 equal to 8 by 3, y1 equal to 10 by 3 and objective function is 44 by 3. So let us go back, x1 is 8 by 3, 24 by 3 plus 20 by 3 is 44 by 3. So this is the LP optimum for this problem. So we right now do not require these intermediate iterations, we need only the LP optimum table. So we set up the first we verify whether the LP optimum satisfies the condition that y1 is integer. So, it does not satisfy the condition that y1 is integer, therefore, we will use the branch and bound algorithm to try and get to the optimum solution that has y1 as integer value. Right now y1 takes a value 10 by 3 which is a non integer value, therefore, the LP optimum is not feasible to the MILP and therefore, we need to go to the branch and bound algorithm. So, we start with the branch and bound algorithm with the LP optimum as the starting node, which has, this is LP optimum, which has x1 equal to 8 by 3, y1 equal to 10 by 3 and z is equal to 44 by 3. Now, as we do in the all integer branch and bound algorithm, we take that variable which should be having an integer value, but right now having a non integer value, which is y1, which is the only variable in this particular example, and y1 is 10 by 3. So, we take the lower integer value of 10 by 3 and we take the upper integer value of 10 by 3 to get 3 and 4. So, we branch off with two branches, which is y1 less than or equal to 3 and then we branch with y1 greater than or equal to 4. So, we have two branches, y1 less than or equal to 3 and another branch with y1 greater than or equal to 4. And because it is a maximization problem, the linear programming optimum LP optimum is an upper bound to the MILP optimum, because what we are essentially doing is we are trying to create nodes by adding constraints. So, you add a constraint to a maximization problem, the value of the objective function will only reduce. So, the LP optimum will be an upper bound to the IP optimum in case of maximization. In case of minimization, the LP optimum will be a lower bound to the IP optimum. We are now solving a maximization problem. So, 44 by 3 is an upper bound to the optimum to this, which means the optimum to this will have a value less than or equal to 44 by 3, cannot exceed 44 by 3. So, we now have this constraint that is added, which is y1 less than or equal to 3. So, we now solve a problem which has all this plus the condition y1 less than or equal to 3. Now, this can be done in many ways. You can solve the linear programming problem from the beginning by adding y1 less than or equal to 3 here, that is one way to do it. The other way to do it is you keep the LP optimum, since we have it. Now, we add a constraint to the LP optimum, which is y1 less than or equal to 3 and perform a sensitivity analysis where we add a constraint and we can do that. The third, of course, is to use simplex method for bounded variables, because y1 less than or equal to 3 is an upper bound on y1. So, we could use simplex method for bounded variables and use it without adding a constraint. You can still use the ideas from the bounded variables to get the solution. Right now, since we are working this out on the board, it is a little easier for us, since we have the LP optimum solution here, it is easy for us to try and use this as an additional constraint into the problem and then solve it. So, let us do that. So, we are trying to introduce a constraint y1 less than or equal to 3. So, our constraint is y1 less than or equal to 3. From this, y1 is equal to, y1 is a basic variable. So, y1 is equal to 10 by 3 plus 1 by 3 x4 minus 5 by 3 x3, that is your y1. And since we have y1 less than or equal to 3, so we are going to have this less than or equal to 3. Now, take this to the other side, you get 1 by 3 x4 minus 5 by 3 x3 is less than or equal to minus 1 by 3, less than or equal to minus 1, 3 minus 10 by 3 is minus 1 by 3. Now, add a slack variable which is x5. So, 1 by 3 x4 minus 5 by 3 x3 plus x5 is less than or equal to minus 1 by 3, x5 greater than or is equal to minus 1 by 3. Now, the slack variable is added to convert the inequality to an equation. Now, from this you can write x5 is equal to minus 1 by 3 minus 1 by 3 x4 plus 5 by 3 x3. So, writing here introduce new slack variable x5. So, x5 is minus 1 by 3 minus 1 by 3 x4 minus 1 by 3 x4 and plus 5 by 3 x3. So, minus 5 by 3 here. So, now we have added the y1 less than or equal to 3 constraint into the simplex table to get this node. Now, if you look at this table is dual feasible, primal infeasible. So, we have to do a dual simplex iteration by sending out the variable x5 that leaves first. Corresponding entering variable is chosen based on a minimum ratio, but taken from the other side. So, 1 by 3 divided by 1 by 3, 4 by 3 divided by minus 5 by 3. In a dual simplex iteration, the pivot has to be negative. So, there is only one pivot. So, 4 by 3 minus 5 by 3, this is the entering variable. In a simplex iteration, the pivot has to be positive. In a dual simplex iteration, the pivot has to be negative. So, there is only one negative pivot. So, this will be the one. Now, we enter this variable, we leave out this variable and do the next simplex table to get the LP optimum corresponding to this node. So, x4 remains here, x5 comes here. So, we have y1, x1 and x3. This is the pivot element. So, pivot becomes 1 by pivot. So, minus 3 by 5, divide by the pivot 1 by 5 minus 1 by 5, divide by the negative of the pivot 4 by 5 1 2 by 5 minus 2 by 5. Now, this value will be 44 by 3 minus 4 by 3 into 1 by 5. So, 44 by 3 minus 1 by 15 . 44 by 3 minus 4 by 15 . So, 220 minus 4, 216 by 15, which is 72 by 5. So, that is the value here. Now, this value is 10 by 3 minus 1 by 3, which is 9 by 3 and 3, 8 by 3 plus 2 by 15. So, 8 by 3 plus 2 by 15 is 40, 42 by 15, which is 14 by 3, 14 by 5. Now, this one is 1 by 3 plus 4 by 15, which is 9 by 15, which is 3 by 5. This is minus 1 by 3 plus 1 by 3, which is 0. This is 1 by 3 minus 2 by 15 is 3 by 15, which is 1 by 5. So, this gives us a LP optimum with y1 equal to 3, y1 equal to 3, x1 equal to 14 by 5, z equal to 72 by 5. So, the first thing we observe is the objective function value has come down 44 by 3 is 14.666 and 72 by 5 is 14.4. So, the value has come down. Now, this is feasible to the MILP because the variable y1 which should take an integer value is right now taking an integer value with y1 equal to 3. So, x1 is continuous 14 by 5, z equal to 72 by 5. So, this node gives us a feasible solution to the MILP, feasible to MILP. So, we fathom this node by feasibility because we have obtained a feasible solution to the problem. But we are still not sure whether it is the optimum solution, but it is a feasible solution to a MILP. Now, the given problem is a maximization problem. So, we have a feasible solution to a maximization problem with objective function value 72 by 5. So, a feasible solution to a maximization problem becomes a lower bound to the optimum. Now, the optimum can be greater than or equal to 72.5. From here we also know that the optimum has to be less than or equal to 44 by 3. So, feasible solution to a maximization problem is a lower bound to the optimum. Feasible solution to the minimization problem is an upper bound. So, we have now obtained a node where we have a feasible solution to the MILP and this is a lower bound to the optimum. So, we do not proceed here because we have already obtained a feasible solution. So, we say that we fathom this node by feasibility. So, now we have to look at the other one. So, we will do that as well. So, we will take this. So, we now have to add y1 greater than or equal to 4 to the LP optimum. So, once again we go back, we now have to add y1 greater than or equal to 4 to the LP optimum. So, y1 from this table is 10 by 3 plus 1 by 3 x4 minus 5 by 3 x3 is greater than or equal to 4. So, taking it to the other side, this will be greater than or equal to 4 minus 10 by 3, which is 2 by 3. Greater than or equal to 2 by 3. So, now we add x5 which is a surplus variable. So, 1 by 3 x4 minus 5 by 3 x3 minus x5 is equal to 2 by 3, and then you take x5 to one side, the others to the other side. So, this gives us x5 equal to minus 2 by 3 plus 1 by 3 x4 plus 5 by 3 x3. So, we now add this constraint into the simplex table by having an x5 here. So, x5 is minus 2 by 3 plus 1 by 3 x4, so minus 1 by 3 and minus 5 by 3 x3 here, minus remains. So, minus 5 by 3, so I have a plus 5 by 3 coming here. Please note that minus 2 by 3 plus 1 by 3 x4 minus 5 by 3 x3, there is a minus sign here, therefore, the numbers change. So, once again this is dual feasible and primal infeasible. So, we have to do a dual simplex iteration. So, when you do a dual simplex iteration, this variable goes first, the negative variable goes first. Now, because it is a dual simplex iteration, the pivot element has to be negative. There is only one negative element here in the pivot. So, this automatically becomes the entering variable. Then we carry out the next iteration where x4 comes here, x5 goes outside, minus x5 minus x3, y1, x1, x4. This is your pivot. Pivot becomes 1 by pivot, so minus 3, divide by the pivot, so plus 2 and minus 5, divide by negative of the pivot, so 1, minus 1 and 1. So, this will become 44 by 3 minus 1 by 3 into 2 is 42 by 3, which is 14, 10 by 3 plus 2 by 3, which is 4, 8 by 3 minus 2 by 3, which is 6 by 3, which is 2. The other one becomes 4 by 3 minus 1 by 3 into minus 5, 4 by 3 plus 5 by 3, which is 9 by 3, which is 3. 5 by 3 minus 1 by 3 into minus 5. So, 5 by 3 minus 5 by 3, which is 0. 2 by 3 minus 1 by 3 into minus 5. So, minus 2 by 3 plus 5 by 3, which is 3 by 3, which is 1. So, we seem to be getting an all integer table, but that is only incidental. There is no guarantee that we will get an all integer table. It just happened because all the variables here took integer values, and because of the nature of this problem. So, it is not guaranteed that in an MILP we will get. Sometimes you get an all integer solution, therefore, this kind of a thing also shows up. So, this is the LP optimum with x1 equal to 2, y1 equal to 4 and z equal to 14. So, this is x1 equal to 2, y1 equal to 4 with z equal to 14. So, once again we observe that it is feasible to the MILP, because since we are looking at the MILP, we are going to look only at the y variables, whether they have integer values. It is only incidental that the x variable also has an integer value in this case. So, it is once again feasible to the MILP with objective function value 14, and therefore, presents a lower bound, a maximization problem, feasible solution is a lower bound. So, we do not proceed further, we do not fathom further on this, because we have already got a feasible solution. Now, we go back and check that we had earlier we had a feasible solution with 72 by 5, which was our best solution. Now, we have another feasible solution with 14. So, if this new solution is better than the existing best solution, we will update. In this case, it is not, because 72 by 5 is more than 14, this is exactly 14. So, this solution, even though it is feasible, has not added much value, because we have already identified a feasible solution that is better than this. So, the algorithm will terminate, because there is no more node to branch on, and this will give us the optimum solution with the current best feasible solution is the optimum solution. So, this is the optimum solution with y1 equal to 3, x1 equal to 14 by 5 and z equal to 72 by 5. In a typical branch and bound, it is not necessary that all of them will be fathomed by feasibility. We have seen that in a branch and bound there are three ways of fathoming a node. One is by feasibility, when you get a feasible solution, which is what we got in both the cases, feasible to the MILP. This one is not feasible to the MILP, but this is feasible to the LP. So, when you get feasible to MILP, you fathom by feasibility. Sometimes you will have an infeasible solution by, because you keep adding constraints at every node, there are times you may get an infeasible solution. So, you fathom by infeasibility. And the third is called fathoming by the bound. For example, if this node had not given us a feasible solution to the MILP, but if this node had given us a solution with y taking a fractional value, if it had done so, y taking a fractional value, and this objective function value more than 72, or objective function value same as 14, the objective function value same as 14, but if y had taken a fractional value, say 4.1 or 4.2, and this value is 14, we can still fathom it by bound, because by adding constraints and by proceeding downwards, we will only get values which are 14 or less. We already have a feasible solution with 72 by 5 for a maximization problem. Therefore, this lower bound here, the feasible solution here, will fathom this particular value, because proceeding from here downwards can only give us solutions with 14 or less. So, there is no point in proceeding further, because we already have a solution with 72.5. In this particular example, we are not able to show fathoming by the bound, and we are able to show only fathoming by feasibility, but in general there are 3 ways to do that. So, this is how we apply the MILP algorithm, branch and bound to MILP. The structure is the same, but the bounds and the feasible solutions will change depending on whether it is a maximization problem or a minimization problem. We have to remember that if we are solving a maximization problem, a feasible solution to the MILP represents a lower bound and LP optimum represents an upper bound. If we are solving a minimization problem, a feasible solution will represent an upper bound and LP optimum will represent a lower bound. So, we have to interpret that suitably when we solve for this. Otherwise, this is the same as solving branch and bound for all integer. In a way, it is advantageous, because if this problem were an all integer problem, then every time we have to take care that all the variables should take integer values. So, the number of nodes that we generate will be more. Because it is mixed integer, where some of them take integer values and some of them take fractional values, in a way branch and bound is advantageous, because we have to consider fewer nodes for the branching. So, branch and bound is an advantage when it comes to solving an MILP, and it is very similar to the ILP. So, in some sense the same branch and bound algorithm can always be used for ILP or MILP, depending on how many variables are restricted to be integers, whereas the cutting plane algorithm will be different for the MILP. So, we will now see the cutting plane algorithm for the MILP. We will retain the LP optimum solution alone here. So, now let us look at cutting plane algorithm for MILP. Now, the cutting plane algorithm for MILP is used when the LP optimum is not feasible to the MILP, like in our case where this is the LP optimum. LP optimum, by relaxing this integer restriction, we are getting y1 equal to 10 by 3, y1 should be an integer. So, we need to use a cutting plane algorithm, which means we have to introduce a cut. So, this row will act as source row for the cut, because that is the variable which should take an integer value, currently not taking an integer value. So, this will act as a source row for the cut. So, let us first write a general expression for the cut, and then we will generate the cut using this row as a source row, and then perform iterations to get to the optimum to the MILP. So, typically we will use something like this: yb is equal to b naught minus sigma aij yj minus some sigma aij xj. Now, this would represent the source row. For example, we will write here y1 is equal to 10 by 3 plus 1 by 3 x4 minus 5 by 3 x3 is written in a general form here, with b naught as the right hand side value, and the set of non basic variables can have some variables which are x variables and some variables which are y variables. In a general problem, we may have more than one y variable, more than one x variable. All the slacks and surplus variables will become x variables. So, we would simply have at the end, like we had here, one x variable and one y variable in the basis. We could have some x variables and some y variables which are non-basic. So, we start writing the set of y variables and the set of x variables which are there. So, this will be the general source row equation. Then we rewrite the source row as something like this: sigma Fij Yj plus sigma Aij Xj minus F naught is equal to B naught minus sigma Yj minus Yb. So, let me explain this. I have just written this from a sheet of paper. So, let me explain this to you. So, what we have done here is that we have kept the xj variables as it is and we have brought this to the other side of the equation. So, the Aij xj terms come exactly as they are. The Yb goes to the other side, so there is no problem there. Now, we are looking at these two terms. Now, this one is not integer because this comes from the source row. If you go back, this comes from the source row. Source row is always a variable that is currently having a fractional value, but should be having an integer value. So, B naught is not integer. So, B naught is now written as, but B naught is not integer, it has a fractional component and it is greater than or equal to 0 or greater than 0. Because it has a fractional component, it is greater than 0, because it satisfies these up to this. So, for example, 10 by 3, you cannot have a minus 5 by 3 there, because it comes from a LP optimum. So, B naught is now written as a lower integer component of B naught plus a fractional positive fraction component of B naught. For example, 10 by 3 will be written as 3 plus 1 by 3. 3 is the lower integer value, 1 by 3 is the difference. 3 plus 1 by 3 is 10 by 3. So, lower integer value of B naught will be 3, fractional value will be 1 by 3. So, what we have done is this B naught is written as lower integer component of B naught plus the fractional component of B naught. Fractional component of B naught is called F naught. So, F naught comes to the other side, B naught remains exactly as it is. In a similar manner, for all these Yj variables, right now we do not have any Yj variable there, but if there were a Yj variable, then that Yj variable is written as a lower integer component and a fractional component. It is written as a lower integer component and a fractional component. So, once something is written as a lower integer component and a fractional component, the fractional component is always a positive fraction. For example, if you have 4 by 3, it is written as 4 plus 1 by 3. If you have minus 4 by 3, it is written as minus 2 plus 2 by 3, because you write a lower integer component and then a positive fraction component. Now, that positive fraction component comes to this side. So, Fij Yj, there is already a negative sign. So, the fractional component comes to this side, Fij Yj. So, the lower integer component lies here. So, this is how this particular equation is rewritten from the original equation. Now, what is the advantage of writing it that way? The advantage of writing it that way is this portion is an integer. Now, this portion is an integer because lower integer value of B naught is an integer, Aij's lower integer value is an integer, Yj's have to be integers in the by the given problem, Yb should also be integer because Yb is a basic variable. So, the right hand side portion is an integer, which also implies that the left hand side portion, this is an equation, it also implies that the left hand side portion is also an integer, because it is an equation, even though it has a lot of fractional components. Now, F naught is a fractional component, all these Fij's are fractional components and so on. Now, then we look at Remember yj's are all greater than or equal to 0 and these fij's are fractional components, positive fractions, because these are taken from these terms, and as I said you have a lower integer value of aij and a positive fraction. So these become positive fractions, fij's become positive fractions. You have to be just that bit careful in the sense that there is a minus sign already here. So depending on the term, suppose it is 4 by 3, then it will become 1 plus 1 by 3 and there is a plus 1 by 3 with a minus sign. So when you bring it here it will become plus sign. If aij itself was minus 4 by 3, then aij will become minus 2 plus 2 by 3. That 2 by 3 is a positive fraction term with a minus sign. So when you bring it to the other side it will become plus. So all your fij's are positive fractions less than 1 and yj's are greater than or equal to 0. So in a way this is a positive quantity. Now this one, depending on the coefficient of aij, can be a positive quantity or a negative quantity. So what we do now is we rewrite this as sigma fij yj plus sigma aij xj with a plus sign, indicating that these are positive aij coefficients, plus sigma aij xj with a minus sign, minus f naught is an integer, okay, is an integer. And because this is an integer, it is either greater than or equal to 0 or less than or equal to minus 1. Correct? All right? Right. Now this is a positive quantity, this is a positive quantity. So these two are positive quantities. So you can now write this as sigma fij yj plus sigma aij xj plus quantity. Those two are positive quantities. Should be greater than or equal to f naught, because this is a f naught is a positive quantity, it is a positive fraction less than 1. So this quantity, this left hand side can be written as greater than or equal to f naught. The other one can be written as sigma aij xj with minus should be less than or equal to minus 1 plus f naught, because this is a negative quantity, right, this is a negative quantity. So take this f naught to the other side, you can write this as less than or equal to minus 1 plus f naught. F naught is always a positive fraction less than 1. So minus 1 plus f naught is a negative quantity, it is a fraction, negative fraction less than 1. So the negative part of this should be less than or equal to minus 1 plus f naught. So once we write this, multiply this equation by f naught divided by minus 1 plus f naught. So this will become f naught divided by minus 1 plus f naught sigma aij xj with negative is less than or equal to f naught by minus 1 plus f naught greater than or equal to. Please note that I am changing the sign of the inequality because I am multiplying it with f naught by minus 1 plus f naught. Now f naught is a positive fraction less than 1. So, f naught by minus 1 plus f naught is not 0, it cannot be 0, but f naught by minus 1 plus f naught is a negative quantity, because f naught is a positive fraction less than 1. So, minus 1 plus f naught becomes a negative fraction. So, f naught by minus 1 plus f naught is a negative term. So, since I am multiplying it with a negative term on both sides which is non-zero, the sign of the inequality will change. So, this is how the second one will be. Now, I combine these two. Now, this quantity is greater than or equal to f naught. I am sorry, this has to be rewritten as only f naught, because I am multiplying by f naught by minus 1 plus f naught. So, this has to be written as this. So, this quantity is greater than or equal to f naught, this quantity is greater than or equal to f naught, therefore, the sum has to be greater than or equal to f naught. So, the general MILP cut will now become sigma Fij. So, I am just adding this term here. So, the final cut will become sigma Fij Yj plus sigma Aij Xj plus f naught by minus 1 plus f naught is greater than or equal to f naught. So, I am adding all of them. So, this is called an MILP cut. This is called an MILP cut. So, now what we can do is we can apply this MILP cut onto this source row to see how we are doing. So, let us write the source row here as y1 equal to 10 by 3 plus 1 by 3 x4 minus 5 by 3 x3. So, we are simply bringing all the Aij, Xj's to this side, Yb goes to the other side. So, finally what happens? There is no y term here, there is no y variable here, therefore, this term does not exist, this term does not exist. Now, this is, we need to bring all the x terms to this side. So, you get 5 by 3 x3 minus 1 by 3 x4, we have got this. Now, this is 3 plus 1 by 3, so minus 1 by 3 is equal to 3, correct. So, now you realize that this term is not there, this term is the one that has a positive value. So, your MILP cut is 5 by 3 x3, that comes from here, f naught is 1 by 3. So, 1 by 3 divided by plus 1 by 3 divided by minus 2 by 3 minus 1 plus f naught into minus 1 by 3 x4 minus 1 by 3 x4 is greater than or equal to 1 by 3. This is our MILP cut, greater than or equal to f naught. So, this MILP cut will give us 5 by 3 x3 plus 1 by 6 x4 is greater than or equal to 1 by 3. 1 by 3 divided by minus 2 by 3 is minus 1 by 2, minus 1 by 2 into minus 1 by 3 is plus 1 by 6 x4 is greater than or equal to 1 by 3. So, now we rewrite this, we add a surplus variable x5. So, 5 by 3 x3 plus 1 by 6 x4 minus x5 is equal to 1 by 3, from which x5 is equal to, take this to the other side, minus 1 by 3 plus 5 by 3 x3 plus 1 by 6 x4. So, this will become, when we add the MILP cut, it will become x5 as minus 1 by 3 plus 5 by 3 x3. So, you get minus 5 by 3 plus 1 by 6 x4. So, you get minus 1 by 6. So, minus 1 by 3, minus 1 by 6 and minus 5 by 3. So, now we have added the MILP cut using the source row. Now, we realize that this is primal infeasible and dual feasible. So, this variable will go out, you have to do a dual simplex iteration, this variable will go out. The entering, there are two negatives. So, 1 by 3 divided by 1 by 6 is 2, 4 by 3 divided by 5 by 3 is 4 by 5. So, 4 by 5 is smaller than 2. So, variable x3 will enter the solution and we need to do an iteration, a dual simplex iteration with this as the leaving variable, this as the entering variable. We will do that in the next lecture and continue with the discussion on the MILP.